This is lesson 4 for our chemical reactions unit, and this is focusing on chemical reactions and energy transfer. Make sure you have your student note packet handy so you can take notes and write down your observations. The major question we want to be able to answer in lesson 4 is what types of energy transfers and changes occur during chemical reactions. Thinking about energy transfer, we are going to be revisiting the energy diagrams that we saw during our physical changes unit and thinking about systems and what's included in that system and what things are entering or leaving the system. So a lot of the things that we talked about in the physical changes unit are going to be coming back into play, but now applied to chemical reactions as opposed to just physical changes. We're going to make observations of 2 different chemical reactions and look at things like temperature to see what energy might be moving in or out of the system or changing. So for this, observing steel wool in air, this is our first observation, we're looking for what happens to the temperature during the chemical reaction. So this is a steel wool pad, so you think like Brillo pads if you've seen those. This particular steel wool doesn't have any soap or oil coating on it, it's just the steel wool. And we're going to watch, it's just a 30-second clip, and see what happens to the steel wool as it goes through a chemical reaction. All right, we're going to make a second set of observations, this time looking at Alka-Seltzer tablets placed into water. So we're going to watch this video together of what happens to this chemical reaction. And you're looking for 2 things. 1, what happens to the temperature during the chemical reaction, and 2, what evidence, so what can you observe, what evidence do you have that the carbon dioxide gas given off during the reaction has mass? So it's important to take time to define a system, right? When we discuss energy transfers and changes, we will divide the world into system and surroundings. So if you think about the chemical system, so the chemical system would be when materials are undergoing chemical reaction. The starting materials, so our reactants, as well as the new materials formed, are products. So for the chemical system, it is just the materials that are undergoing the reaction. The surroundings would be everything else, the container, the thermometers, anything else you see in that picture outside of your reactants and products. So let's apply this idea of system versus surroundings for each of our examples that we observed. So let's start with steel wool rusting in air. Was the thermometer representing the surroundings warming up or cooling down during the rusting reaction? Then, did the thermal energy of the surroundings, including the thermometer, increase or decrease when they interacted with the system undergoing the chemical change? What evidence do you have for whether the thermal energy of the surroundings increased or decreased? How can you support that? And then last, during the rusting process, was energy transferred from the chemical systems to the surroundings or from the surroundings to the chemical system? All right, let's take some time and answer a question. Which of the following GR, that's giver-receiver, energy diagrams best describes the macroscopic interaction between the chemical system and the surroundings during the chemical reaction involved in the rusting of steel wool? An important thing to think about here, macroscopic means I could observe it with my eyeballs. And also think about what you recorded on that previous slide where we're looking at whether energy was increasing or decreasing in the surroundings versus in the system. Now, the reaction that you saw with the steel wool is something you may have already experienced in another setting, and that setting is in hand warmers, the chemical hand warmers that you can buy. So the hand warmer contains iron along with some other materials, and when they are activated, a chemical reaction occurs that produces energy. So iron and air combine and form iron oxide, and that energy that is released in the form of thermal energy, and that's why they get warm. There is a limiting factor here, though. Just like we've talked about before, there's a limited amount of iron contained inside the hand warmer. So when that reactant runs out, there's no longer a reaction occurring and you don't have any more warmth. That's why they're a consumable item. They get used up. So a reaction like the one with the steel wool in the air or the chemical hand warmer are both considered exothermic reactions. We have to keep in mind always the law of conservation of energy. To conserve energy, the surroundings must increase in thermal energy. Hence, the thermometer would increase in temperature, or your hands would feel warmer. Exo is an English prefix derived from Latin prepositions, meaning move out or away from. I always think of this as exo is like exit, right? If you exit, you leave, you move out. So an exothermic reaction, you are leaving or losing your energy. A really common example that we've all experienced would be water vapor from the air condensing into liquid droplets, like on a glass or a mirror in your bathroom. This would be an example of an exothermic process because I am losing heat to the environment from my water vapor. Next, let's tackle the second observation set that we made with the Alka-Seltzer tablets in water. So this time, was the thermometer representing the surroundings warming up or cooling down during the Alka-Seltzer reaction? Did the thermal energy of the surroundings, therefore, increase or decrease when they interacted with the chemical system? And what evidence do you have for that increase or decrease? During this chemical reaction, and when the thermometer and chemical system are interacting, Was the energy transferred from the chemical system to the surroundings, or from the surroundings to the chemical system? So which was the giver and which was the receiver in our reaction? All right, let's do an application question. Which one of the following give-receive energy diagrams best describes the macroscopic or observable interaction between the chemical system and the surroundings during the chemical reaction involving the Alka-Seltzer in the water? Now remember, the chemical reaction or the chemical system would be the Alka-Seltzer in the water. And then what would be considered the surroundings? The surroundings would be things like the thermometer, the graduated cylinder or container, right? So make sure you understand the difference between the chemical system and the surroundings as you think about who was the giver and the receiver for this energy transfer. All right, so the chemical reaction that we saw with the Alka-Seltzer in the water is called an endothermic reaction. If we remember our law of conservation of energy, in order to conserve energy in an endothermic reaction, the surroundings must decrease in thermal energy. A thermometer would decrease in temperature, or your hands would feel cooler. Endo is an English prefix derived from Latin prepositions meaning into or within. So think enter. Endo, enter. So when you enter, you move in, right? So boiling water is an example of an endothermic process. I am adding heat into the water from my surroundings, whether that's a stove or a flame, etc. Melting an ice cube in your hand. If I put an ice cube on your palm, the ice cube is going to melt because there's heat leaving your hand and entering the ice cube. That's actually why your hand feels cold, because it's losing heat that's moving into the ice. All right, let's tackle our final summarizing question here. Which of the following processes are endothermic? And this shouldn't be quite as hard as it could be because I kind of just explained one of these. But think about endothermic means energy is entering the chemical system from the surroundings.